Hello, I'm Murayama, Chiba Children's Hospital in Japan. First, I would like to thank the organizer for giving me an opportunity to talk today. My title is Clinical and Molecular Basis of Mitochondrial Disease and Treatment. If we define mitochondrial disease, mitochondrial disease is a collective term for many different clinical disorders united by a failure of mitochondrial function and energy production. Each of our cells has mitochondria, which played an important role in creating ATP and various cellular metabolic pathways. And also more than 1,000 proteins in mitochondria are encoded by both mitochondrial and nuclear genome. That's why mitochondrial disease can develop in any organ, any symptom, any age, and any mode of inheritance. There are three types of heterogeneity in mitochondrial disease. One is functional heterogeneity, that respiratory chain subunits are coded by mitochondrial DNA and nuclear DNA and has complex mechanisms to function the oxidative phosphorylation. And second is molecular heterogeneity, that mitochondrial DNA has 37 genes and code 13 proteins. And nuclear DNA has more than 20,000 genes and code up to 1,200 mitochondrial proteins. Third is clinical heterogeneity, that mitochondrial disease can be occurred many symptoms, including neurological and non-neurological symptoms. This is the number of mitochondrial disease patients diagnosed by enzymatically or genetically from 2007 to 2019. First 7 years, we are doing enzyme analysis first, but recently we have changed from enzyme first to gene first. This is our data. We have collected the patient sample from all over Japan. Totally 3,000 cases samples are collected, and we did definitive diagnosis based on biochemical approach, 1,760 cases. After biochemical approach, we did a gene panel or whole exome sequencing. Also, recently we directly gene panel and whole exome sequencing if mitochondrial disease are suspected, like Lee syndrome. After that, we will undergo the multi-omics analysis, including whole genome analysis and RNA sequence and proteome approach. This is a breakdown of clinical diagnosis. About half patient is muscle and nerve phenotype, including Lee syndrome and neurodegenerative disorder and mitochondrial cytopathy like MERS. And about 16% is neonatal onset mitochondrial disease, and 10% is hepatic disease, and cardiomyopathy type is 8%. This is the list of genetically diagnosed mitochondrial patients in Japan, totally 480 patients. Most common causative gene is MTTL1, including 3-243-8G mutation like MERS. And then second is ATP6, followed by PDHA1. For the phenotype, Lee syndrome is the most common, 164 patients. And this is a frequent nuclear encoded gene in Japan and the US. POLG1 is the most common in US. On the other hand, POLG1 is very rare in Japan. Only 4 cases had been diagnosed so far. Recently, we published some type of mitochondrial disease about genotype and prognosis. This is Leigh syndrome, and this is mitochondrial hepatopathy. This slide shows the difference in prognosis depending on the time of onset of Leigh syndrome. In red, patient with disease presentation before 6 months of age. In blue, the patient is late onset. Onset before 6 months of age was a risk factor for survival outcome. This slide shows the survival status and the clinical condition of the patient with major genetic background. So X1 patients are all bedridden. SAF1 patient is 6 patients are alive, but 3 patients out of 6 patients are using mechanical ventilation. In mitochondrial DNA, some patients are died in ATP6 and ND3, ND5, and ND6. Especially ND3 patient among 6 alive patients, all is bedridden, and 5 patients are using mechanical ventilation. This is the distribution of onset age in months according to causative gene. Patient with mutation in ND3 and patient with 8993T2G mutation had the earliest onset. X1 deficiency had relatively early onset among nuclear DNA group. Patients with other mutation in ATP6 or deficiency in NDUFAF6 or SAF1 showed later disease onset age with wider distribution. Genotype and severity in Leigh disease. Among patients with genetic diagnosis that shows a narrow distribution of onset age, those who died and those who are still living could not be distinguished by the onset age. On the contrary, for patients with NDUFAF6 deficiency, later onset was related with better outcome. The mean onset age of NDUFAF6 patient living with head control intact was 42.2 months compared to 9 months of patients either deceased or who had lost head control. This slide shows the molecular diagnosis of Leigh syndrome in genomic countries and Japan. Overall, ECHS1 is common nuclear gene-related Leigh syndrome in genomic and Japan. So therefore, the natural history of ECHS1 is important for future clinical trial. So recently, some countries' researchers published the Leigh syndrome natural history and molecular feature: China, Italy, UK, and Japan. This data is very useful to provide valuable information of the patient in front of us and useful to consider the mitochondrial medicine. We are playing important role as a partner countries in genomics, and I have great expectation for development of mitochondrial disease research. International collaboration is very important for molecular diagnosis and mitochondrial medicine. We are establishing the Japanese Mitochondrial Disease Research Center and connecting with not only Japanese hospital and university, but also Asian, European countries, US and Australian mitochondrial disease researcher. We discovered the novel gene through international collaboration and also novel gene alone in Japan. Next, I will talk about the mitochondrial hepatopathy. We published the paper of Japanese mitochondrial DNA depletion syndrome and the outcome of liver transplantation in 2020. Again, I show this slide. About 10% were mitochondrial hepatopathy. Among them, about 25 cases were hepatocerebral mitochondrial DNA depletion syndrome. These are the causative genes in mitochondrial hepatopathy. Green curve represents mitochondrial DNA depletion syndrome, accounting for 60%. Most frequent gene is MPV17. Second is IARS-ERS. Then the third is the DGOK. Right is a prognosis by causative gene. Green represents alive. About 60% of hepatopathy patients die so far. Compared by MTDPS or non-MTDPS, MTDPS group showed obviously lower survival rate. I will talk about the liver transplantation in mitochondrial disease. The 5-year survival rate after liver transplantation is around 90% in all liver disease. But in mitochondrial disease, 5-year survival rate is 30% due to post-liver transplantation deterioration of neurologic and extrahepatic symptoms. So, liver transplantation for mitochondrial disease may be considered in patients with isolated liver disease. But actually, it is very difficult to exclude the development or deterioration of extrahepatic manifestation before liver transplantation. This slide shows the frequency of liver transplantation of mitochondrial hepatopathy in Japan. Liver transplantation has been performed on 13 patients with mitochondrial hepatopathy, mostly for MPV17 patients. The reason for liver transplantation are liver failure for 9 cases, hepatocellular carcinoma for 2 cases, and cirrhosis for 2 cases. The right chart shows the prognosis after liver transplantation. Green represents survival case. 4 out of 9 MPV17 patients survived. I'd like to introduce severe MPV17 cases. A Japanese boy had growth failure, jaundice, and white stool at 40 days of age. Biliary atresia was suspected at clinic. Then he was referred to university hospital. He had jaundice and hepatomegaly without any neurological findings. Blood test revealed elevated liver enzyme, bilirubin, and lactate. He was diagnosed with liver failure. Liver biopsy was performed at the age of 60 days. His liver pathology showed macro and microvesicular steatosis and fibrosis in portal area and pericellular fibrosis. Enzyme analysis revealed the liver had RC complex 1, 3, and 4 deficiency, and the amount of mitochondrial DNA was decreased to 8%. Then the Sanger sequencing identified pathogenic variant in MPV17 gene. he was diagnosed with MPV-17 related hepatocellular mitochondrial DNA depletion syndrome. For the clinical course, some vitamin and lipid-rich diet and sodium pyruvate were administered. His liver function was temporarily getting improved, but he got fever after regular vaccination and developed liver failure at 4 months of age. He received living donor liver transplantation. He had remarkable ascites and significant edema. Histology of the isolated liver was severe steatosis and fibrosis. After liver transplantation, a part of his small intestine was resected because of unknown recurrent intestinal bleeding. He died of pulmonary hypertension at the age of 21 months. Then, I focused on correlation between genotype and prognosis after liver transplantation. These are patients who were genetically diagnosed with hepatocellular form of mitochondrial DNA depletion syndrome. The blue means deceased cases. Except MPV-17 patient, all cases were deceased. In MPV-17 cases, this frame shift variant highlighted in yellow was seen in 8 of 13 patients. This frame shift variant was also reported from Korea. This suggests liver transplantation should be avoided in this genotype. We published the liver transplantation for MPV-17 in last year. This slide shows the macroscopic and pathological findings of mitochondrial hepatopathy due to MPV-17 patient. 451 duplication C mutation, frame shift mutation. The histopathological findings shows macrovesicular steatosis, giant cell hepatitis, and fibrosis with hepatocanalicular cholestasis. Macroscopic findings shows avocado-like liver, which is G-specific MPV-17 mutation, and indicates the poor prognosis for liver transplantation. And we also compiled the data and published the neonatal onset mitochondrial disease and mitochondrial cardiomyopathy in last year. I will talk about cardiomyopathy. This slide shows the prognosis and the genetic background of mitochondrial cardiomyopathy in our cohort. 223 patients out of 2,437 patients, consecutive mitochondrial disease patients who were genetically confirmed were enrolled. So cardiomyopathy were observed 21% of total, and HCM was most frequent, followed by DCM and LVNC. And nuclear DNA mutation were found in 54%, and mitochondrial DNA mutation were found in 30% of cases. This result is in contrast to that of adult cases, where nuclear DNA mutation were found in only 4% of cases. This slide shows the genetic background of mitochondrial cardiomyopathy. For HCM, BORA3 being most frequent, followed by ACAD9, QRSL1, and GTP-BP3, and so on. In mitochondrial DNA mutation, genetic defect in MTND5 was highest, followed by MTTL1 and ATP6 and 8. Interestingly, de novo duplication in ATAT3A to C cluster region caused perinatal lethal cardiomyopathy and was recently identified by our international collaboration. For DCM, nuclear gene defects were prominent, and thus TAZ was highest, followed by NDUFB11 and TMEM70. This slide shows a Kaplan-Meier estimate of overall survival for mitochondrial disease patients with or without cardiomyopathy. As shown here, the prognosis is significantly worse in patients with cardiomyopathy than without cardiomyopathy. This table shows prognostic factors associated with all-cause mortality. Multivariate analysis demonstrates that the three factors highlighted in blue, that is neonatal onset, chromosomal aberration, and HCM, were independent factors for raising mortality. The Kaplan-Meier curve indicates that if HCM is combined with neonatal onset or chromosomal aberration, this occurred much earlier than in presence of HCM alone. This is a clinical trial and the outcome measure in Japan, and sodium pyruvate is for MERS and Rh syndrome. The result is withdrawal. Taurine for MERS is approval. I will talk later. And 5-ALA plus sodium ferrous citrate for all mitochondrial disease, result is withdrawal in this year. And EPI743 batchikinone is for mitochondrial disease seizure, is now ongoing. I will talk later. So I will talk about the taurine therapy for MERS. Most of MERS are caused by mitochondrial DNA mutation, especially 3243A2G mutation is the most common point mutation encoded tRNA leucine. Taurine modification for tRNA anticodon, not only UUA but also UUG are recognized leucine under taurine modification. So, taurine modification defect occurs in MERS. For example, 3243 mutation occurs taurine modification defect, and therefore mitochondrial protein synthesis defect. So, impaired taurine modification, therefore high-dose taurine treatment improves these taurine modification. This is a paper of taurine supplementation for MERS, multi-center open label 52-week phase 3 trial, published in 2019. So this is design for clinical trial. Multi-center open label study phase 3, and subject is MIRAS patient with recurrent stroke-like episode. And the patient and the period is a 10 patient, 52 weeks. And inclusion criteria, stroke-like episode, more than 2 episodes within 78 weeks before enrollment, and more than one episode within 52 weeks before enrollment, and then totally 52 weeks taurine therapy. So this is a chart of clinical course, and so stroke-like episode is apparently decreasing each patient. Therefore, taurine therapy was approved in Japan. And this is a Japanese newspaper, 22 February 2019. This taurine therapy is the first approved drug for mitochondrial disease. Next, I will talk about two C's, apomorphine and MA5. I will introduce the apomorphine researched by Professor Osaka in Jichi Medical University. Apomorphine was selected from chemical library and examined chemical library using fibroblasts from patients with mitochondrial disease. Apomorphine is a dopamine agonist used as a rescue therapy for off period of advanced Parkinson's disease. Rapamycin, an inhibitor of the mTOR pathway, improves the survival of mouse model of Lee syndrome. mTOR affects the mitochondrial activity by regulating mRNA translation and other metabolic processes. mTOR inhibition by apomorphine may be related to therapeutic effect. So recently, the continuous administration was reported to improve not only the motor symptoms but also non-motor symptoms in Parkinson's disease patients. Mitochondrial dysfunction has been shown to be related to Parkinson's disease, and it is getting attention as new target of treatment. So apomorphine may be beneficial for Parkinson's disease as well as mitochondrial disease. So apomorphine protects against oxidative stress and increase mitochondrial respiratory activities. And GDF15 biomarker of mitochondrial disease was significantly decreased by apomorphine, and apomorphine is suitable for repositioning toward mitochondrial disease. So now developing by Professor Osaka. I also introduced the drug development of MA5. MA5 mitoconic 5 make ATP by connecting with mitofibril and accelerating polymerization of ATP synthesis. MA5 was researched by Professor Abe's group in Tohoku University. This slide shows the improvement of survival curve of the patient fibroblast using the MA5. Lee syndrome, MIRAS, and liver and cancer syndrome survival curve is getting better. And now phase 1 finished. Now Professor Abe is struggling hard toward phase 2. Finally, I introduced a patient group in Japan. There are two patient groups in Japan, and they lobbied the Yokohama city to turn Yokohama Port Opening Memorial Hall building green during World Mitochondrial Disease Week. Patient group is strong partner for mitochondrial research, including mitochondrial medicine.
And this is our collaborator, Chiba Children's Hospital, my colleague, and Saitama Medical University, Professor Akira Otaki, and the VIυπάρχN group, and Juntendo University, Professor Yasushi Okazaki's group, and Helmholtz Center in Munich in Germany, Holger Prokisch group, and Murdoch Children's Research Institute in Melbourne in Australia, David Soban's group, and Ahmed Murayama's group. Thank you for your kind attention.